So let's do this example 1611, finding the equilibrium partial pressures from K and initial partial pressures. So instead of concentrations in this one, we have partial pressures. Consider the reaction, iodine reacting with chlorine to form 2-iodine chloride. Reaction mixture at 25 degrees Celsius initially contains both reactants, each with a partial pressure of 0.150 atmospheres, and no product. Find the equilibrium pressures of all three substances. So this is an equilibrium problem. We're given Kp, the equilibrium constant with respect to pressure. So we need to make an ice table. Ice, baby. I think we need a soundtrack is what we need. Equilibrium. Oh, well, that's not very good. There, that's better. So, what are the initial partial pressures? .150 for the reactants, right? And 0 for the product. Well, what's going to happen as this reaction proceeds? The reactant pressures will decrease. So let's call this one minus X. And then Cl2 will decrease by how much? Minus X. And our product will increase by how much? Plus 2X. Is everybody seeing how I'm doing that? Okay. So then we just add the I and C rows, and we've got 0.150 minus X, 0.150 minus X, and 2X. So our equilibrium expression here, these aren't concentrations, they're pressures, but it's the partial pressure of ICl squared divided by the partial pressure of I2 times the partial pressure of Cl2. Same form. So they gave me Kp was 81.9, and so that's going to equal the expression for that product squared divided by the pressure for I2 times the pressure for Cl2. Well, they are the same. So I could put in that this is 0.150 minus X squared. Yeah, those balances sound like cows mooing. Now, we can certainly put this in our solver and find the answer. This one actually, though, you can solve without doing a quadratic equation. If you notice that both of these things are squared, if you take the square root of this side and the square root of that side, you're just going to end up with X terms. I still don't feel like dealing with it, but you can do it that way. So I'm going to put 81.9 on the left side, my equal sign. And the quantity 2x squared divided by the quantity 0.15 minus x squared. Survey says 0.12285. Anybody else get that for X? Okay, cool. So let's put this into these expressions and make sure that it's going to work. So if I have 0.15 minus x, 0.15 minus 0.12285, that's still going to be a positive number. So these are both going to be positive numbers, and this is going to be a positive number, so it's going to be okay. So we want the equilibrium pressure of all three substances. So the pressure of I2 is going to equal 0.150 minus, I think I'll just round that to 0.123. .027 atmospheres. And that's going to be the same for the Cl2. They started at the same, and they have the same coefficients in the chemical equation. And then ICl is 2 times that. So there's my answers. Any questions?
I didn't get that answer when I put it in the calculator.
What'd you get?
0.791. And I was supposed to get that, yeah.
So this brings up a good point. He had the equation entered into his solver correctly, but he was getting a number that was 0.7 something, right? So if that's the number you get first, well, we have to check and make sure that it's going to work. 0.150 minus 0.7 something is going to give me a negative pressure, right? That's going to be less than 0. That's impossible. So that is a correct root. Apparently, it's hard to see how, but it's a correct root for that equation, but it's not the correct root for the example. So then we have to look for another root. Okay, and so you look for a different root by starting at a different number. Any questions? Other questions? Okay, so now that we've talked about the solver and how to do things, it's not exactly the hard way, but it does involve using a calculator, one that can solve problems for us. In some equilibrium problems, there are approximations that we can make that greatly simplify the calculation without affecting the accuracy much. So if K is small, that means that the reaction doesn't go very far to the right. It doesn't make much product. If the initial reactant concentration is large, then we can assume that the change is going to be small because K is small, and subtracting a small number from a large number doesn't really matter. So we can check the assumption by comparing the calculated value of x, the value that we end up with, to anything that we're subtracting x from. And it should be 5% or less than the number we're subtracting it from. Okay, so I've said all that, and I'm pretty sure none of it made any sense. Because if you don't know what I'm talking about, then you wouldn't know what I was talking about. So let's talk about something more specific. So here we have A going to 2B. The equilibrium constant is small, 3.3 times 10 to the minus 5. The initial concentrations are 1 molar and 0. What are the equilibrium concentrations? So the initial concentration for A is 1. The initial concentration for B is 0. A is going to change by minus x. B is going to increase by plus 2x. And so here we've got 1 minus x and here we have 2x. The x is small approximation says, well, when we're subtracting x from 1, it's small enough that it doesn't matter. So we can put in, we've got our equilibrium constant is equal to, and we've got 2x squared in the numerator and 1.0 minus x in the denominator. Small equilibrium constant, x is going to be small. So subtracting a small number from 1.0 might not make much difference. It's like, well, how could that be? Well, let's say you're driving, you're trucking for a fruit company in Wrigley, and you've got the load of oranges, and you pull onto the scales, and you get the weight, and then, you know, off you go, and one orange falls off. Oh no. I've got a ton of oranges, and I just lost one that weighs less than a pound. Does that even matter? No, it doesn't. It's so small that it's insignificant, right? Kind of like electrons. Yeah. So let's see what happens here. What we're going to do is we're going to say, well, x is small, so I can ignore it. So that makes the math a lot easier, because with x is small, now I've got 3.3 times 10 to the minus 5 is equal to 2x quantity squared, which is 4x squared. So if I divide both sides by 4 and take the square root, I come up with x is equal to 0.00287. Is that small with respect to 1? It is. I mean, thinking about significant figures, the way this number is written indicates that there's uncertainty in the ones place. My x doesn't even have any digits until the third decimal place, right? So how we need to check that it's valid, and so what we're going to look at is this x 5% or less than the number I subtracted it from? So 0.00287 divided by 1 times 100 is 0.287%. It's less than 1%. And so the approximation is valid. Any questions?
We always divide it by 1?
Well, it depends on what your starting numbers are.
Okay, so it's by the initial concentration.
We're going to divide it by the thing we're subtracting x from.
Oh, okay.
So 1 minus x. I need to make sure that x is less than 5% of what I'm subtracting it from. And that's a guideline, right? Not a hard and fast rule, but it's a guideline.
When should you even bother using this approximation? Is it only when k is small?
Yeah, usually when k is small, because if k was large, then my changes would be very large, right? And it's not going to be small.
Because it's not always going to be valid.
No, it is not always valid.
So like the previous problem we just did, it was 0.150 minus x.
Mm-hmm.
So we can assume that it's going to be small.
Well, we actually solved that, and we came up with x being 0.12, right?
Right. That's what.
And so 0.12 is more than 5% of 0.15. The number that it's being subtracted from.
And so, but how do I know that beforehand? I don't, right?
You,
So that
you
means-
don't. No, you don't. You can get an idea based on the size of the equilibrium constant and the initial concentrations. If this initial concentration was 1 times 10 to the minus 4, well, then X is going to have to be really, really, really small, right, in order for it to be small relative to my initial concentration. If you're good with your solver and you like using the solver, you can use the solver for everything, it's fine. But if you don't have a solver, a lot of the problems in the book do end up working fine with the X's small approximation. Or you could use the quadratic equation. So let's do a real example. We're going to do a couple of examples here. Here we've got decomposition of hydrogen disulfide into its elements. Here our Kc is 1.67 times 10 to the minus 7, so we see that that is a small equilibrium constant. Our reaction mixture contains 0.1 molar of the hydrogen disulfide and of the hydrogen to start with, and 0 of the S2, and it wants us to find the equilibrium concentration of S2. So I'm going to make an ice table. So I've got 2H2S is in equilibrium with 2H2 and S2. Got my initial change, equilibrium, put in the initial values. I have 0.100 molar of that. I have 0.100 molar of the H2, and I have none of the S. So am I going to, is this reaction going to proceed to the right or to the left? To the right. To the right. To the right. Because S is 0. It can't go to the left because there's no S to react. So the S is going to change by plus X. What's the H2 going to change by? 2X. And how about the H2S? Minus 2X. Okay? So then we have 0.100 minus 2X. We have 0.100 plus 2X. And we have X. So our equilibrium constant, 1.67 times 10 to the minus 7. That's going to equal the products, 0.100 plus 2x squared times x, divided by reactants, 0.100 minus 2x squared. Any questions?
Are you about to cancel some things out?
Yeah, we're going to cancel some things out. So if we use the X's small approximation, it does not mean that we get rid of all the X's. We're removing X's that are added or subtracted with another number. So here I have 0.1 plus 2x. If X is really small, it's like adding 2 oranges to the big truck. Doesn't matter. If X is really small, it's taking 2 oranges away. Doesn't matter. So the X's small approximation is going to get rid of those guys right there. We're going to say X is small enough that we don't even need to consider what it is subtracting it from 0.1. Well, that makes the math a lot easier, doesn't it? Because these values cancel out. And I'm left with X is equal to 1.67 times 10 to the minus 7.
It's a really nice problem.
Isn't it? It's almost like it was set up to be that way. 1.67 times 10 to the minus 7th. And that would be the concentration of S, but we have to check the 5%. So 1.67 times 10 to the minus 7 divided by what I subtracted it from. Whoops. Times 100. And I think this ends up being 1.67 times 10 to the minus 4.
Wait, when you look at 0.10, I thought you canceled out.
This is my check to see if the approximation is valid.
Oh.
What I'm looking for is something smaller than 5%. It's definitely smaller than 5%. So X is small, approximation is valid, and so this is the concentration of S2 at equilibrium, which is what it was asking me for. Any questions?
Now say it was plus 2x. Just find the concentration, we would just multiply by 2.
Yes. Yep. Yeah, so once you determine what X is and that X is truly small, then you just put X in wherever you need. It didn't ask us about these concentrations. We could find out anyway. So over here, this one is going to be 0.1 minus 2 times 1.67 times 10 to the minus 7. And that's 0.099996. What does sig fig say? That's 0.100. Really hasn't changed. Any questions about this one? Mm-hmm.
I'm sorry, can you explain one more time why, just the calculation on the bottom right? Why
This one?
That's right.
So what I'm doing down here, you see that? Kind of. Very pale highlight green. I am checking that the approximation is valid. So this percent that I came up with, that's less than 5%. I'm okay. If that was greater than 5%, I cannot use the X is small approximation. I need to go through with all the math.
5% of
5% of whatever it's being added to or subtracted from.
Would that always be the same?
No.
So you might have to check for 2? You might
So
have to-
that's an excellent question. What if these numbers are not the same? What if this is 0.1 and the other one's 0.15? I'm going to look at whichever one is going to give me the larger percentage. So I'm going to compare it to the smallest one. Yeah. It usually doesn't come down to that, but question?
Yes, can you re-explain to me why X is small?
Explain why X is small. So I just said I'm going to pretend that X is small, right? And so I'm ignoring this, and when I calculate X, I find out that this way, calculating X, it is a very small number,
Okay.
right?
I see.
And exactly how small it is important. We're concerned with how small is it relative to these concentrations. It's very small compared to 0.1. Why would I even think to do that? I'm looking at this very small equilibrium constant, which tells me the reaction is not going to change very much. It's not going to go very far. So it's a possibility that X will be small. Did you have a question?
Yeah, so like on an exam, and you asked for us to do approximation, you're probably gonna ask us to do approximation.
I might, yeah.
And So if we put it in our calculator and I come up with 1.67 times 10 to the negative 7, I can go ahead and just divide that by my concentration and times it by 100 and do it that way. And if it's less than 5%, I can say it's okay. Or do I have to do the math like that?
That's a good question. So would you have to show that you know how to do this on an exam?
Right.
It's possible. I could make you, write it out, show the calculation using X is small without putting it into your calculator solver. I probably won't do that because I don't care that much. So the X is small approximation used to be a really, really big deal because if you had a messy equation that didn't fit the quadratic equation, it was a booger to solve. I mean, you either had to go to the VAX computer that took up a whole building and get some time and punch some cards, or, do a whole bunch of iterations by yourself, which is super tedious. But we don't have to do that anymore. Right. As we noticed here, though, this X is small approximation with these things that canceled out, I think that was faster than plugging it into the calculator. Yeah. So it kind of depends on how comfortable you are with your calculator.
Sorry, but I'm kind of confused why you're able to cancel out the two x's. Is it because they're being added and subtracted to
Yes,
one
I am
another?
saying they are so small that adding 2 of them to 0.1 and subtracting 2 of them from the other 0.1 does not significantly change the value. It's still 0.1.
It's technically like it's squared, so it's not just subtracting 2x.
But the difference here of 100 plus 2x, if x is 10 to the minus 15, and I add it onto 0.1, my calculator can't even show that to me because the difference is more than 9 digits apart.
So if you find that x isn't less than 5%, does that mean you can't cancel?
That's right.
So you would have to go back.
Yeah, so if you do this and find that x is more than 5%, then you have to solve it the full way. Let's do an example like that. Same chemical reaction, same equilibrium constant, different starting concentrations. So again, we've got 2H2S in equilibrium with 2H2 and S2. We're making an ice table. So my initial concentration of H2S is 1.00 times 10 to the minus 4, and both of the products are 0. Now this obviously has to go to the right. This is going to decrease by 2x, that will increase by 2x, that will increase by x. This change row is the same as on the previous problem. So here I have 1.00 times 10 to the minus 4 minus 2x. I have 2x and I have x. So I take my equilibrium constant, 1.67 times 10 to the minus 7. That's going to be equal to 2x squared times x divided by, not 0.1, 1.00 times 10 to the minus 4 minus 2x squared. It's really easy to forget those squares. The x is small approximation says that we're going to get rid of this subtracted term. Say it's too small to mess with, so I can, anything that's subtracted or added with x, I can just get rid of those. And now we solve the rest of this. So I'm going to multiply both sides by 1 times 10 to the minus 7. Sorry, 1 times 10 to the minus 4 times 1.67 times 10 to the minus 7. and I'm going to get 1.67 times 10 to the minus 11 is equal to what's on the top here. So 2x, the quantity squared, is 4x squared, and there's another x, so this is 4x cubed. Divide by 4.
Did you meant to put -7 on the left-hand side of that?
I multiplied by this.
Oh,
So this is the original equation, and now I'm simplifying it and kind of writing down partial work.
Does that square goes away to the squared at the bottom part?
No, it doesn't. Thank you. I lost that.
Yeah.
So, yeah, I screwed up. I can't lose that. So let's start that again. 1.67 times 10 to the minus 7 times 1 times 10 to the minus 4 squared. So that is actually 1 times 10 to the minus 15. It's a little different. So I'm going to divide by 4. The 4's cancel out. And now I'm going to find out that x is equal to the cube root of 4.175 times 10 to the minus 16. Seven 7.47 times 10 to the minus 6. Yes.
so what's keeping us from just putting this whole thing in our calculator?
Nothing.
Okay.
Absolutely nothing.
Okay. Just
Mm-hmm.
What was it that you crossed out right there in red? I didn't get to see it.
That was this minus 2x.
Just to confirm, under 2x, it's 2x because of the coefficient 2.
Yes,
And then over on the top right, it's 2x squared.
because of the
Squared
coefficient
also
2.
because of the
Yeah. Yeah, so let me make a little space. So if we just write the expression, Kc is equal to h2 squared s2 divided by h2s squared. So, any questions about how I got x to be that? So, are we just done?
Oh, I mean, we got to put it in.
We have to check and make sure that it's valid. I mean, this x it looks really small. Isn't it good? We gotta check. So, 7.47 times 10 to the minus 6 divided by 1.0 times 10 to the minus 4 times 100. That's bigger than 5, right? That's why you have to check. You shouldn't just eyeball it. If we use this approximation, our calculations are going to be off.
So you only figured that out after you already did that?
Yeah.
Super lesson.
Well, yeah. It's in the book, so I'm teaching it to you.
Yeah.
If you were not allowed to use a calculator with a solver, you'd have to be able to do this.
Are we allowed to use a calculator with the solver on the final?
You are, yes, just not a programmable calculator.
Yeah, sorry.
So yeah, these are fine. Because the reason for that limitation on the ACS exam is not because of what you can do with the calculator to do better on the exam. It's in what you can, information from the exam you can take out and give to other people to cheat on the exam. So it's for the security of the exam. Yeah. Yeah.
Can you just like reset the calculator when you leave?
Well, in theory, yes. Yeah. Mm-hmm.
So we could, I mean, the reason we would go through this in like homework or a test, if we preferred not doing this way, we'd probably get a question that says like something's not valid, figure out the percent of.
There could be something like that, yeah.
Okay.
So you should have an acquaintance with how to do a problem like this.
Okay.
You should say, well, oh, okay, I see, yeah, that's not much of a difference and it's coming out to be the same, and okay, I don't care to do it that way, but, you know, there it is. Yeah, I'm not going to really force you to do this. So what do we do now? Well, you got to use our solver and actually do the problem. So I have to put this back in, this minus 2x. So I'm going to go to my solver and type this in. So I got 6.78 times 10 to the minus 6. Now, are those numbers close? Yeah, but close only counts in horseshoes and hand grenades. So the equilibrium concentration of S2, again, ends up being X, and so that's our answer right there. Any questions? Mm-hmm.
And I understand the solver makes this totally irrelevant.
Mm-hmm.
But does something funky where they take that approximation that you get, even though it's wrong, it's greater than 5%, and they plug it back into the equation for K. What are they doing there?
They might be doing some kind of an iteration.
Okay.
Yeah. Apparently I didn't reread that part of the book.
It's example 15.13, and
So here's a conceptual problem about this. We've got a generic reaction, A goes to B. Consider each value of K and initial concentration of A. For which set of values does the X is small approximation most likely to apply? Is the most. For which set of values? Yeah, there's a grammar mistake there, but let's not get distracted. Well, what helps X is small? Should the K be large or small? Small. So that looks like we want either A or B, because those are the two small Ks. And then we want any initial concentrations to be large or small? Large. Because the larger this is, the less effect subtracting or adding something to it will be. So the answer is A. So some notes. Concentrations must be expressed in moles per liter. Partial pressures must be in atmospheres. You need to use the appropriate equilibrium constant, Kp or Kc. Moles may be used in place of concentration or partial pressure only when the moles of reactants in the chemical equation is equal to the moles of products. The X is small approximation does not mean that X is 0. X is never 0. It might be, 1 times 10 to the minus 57. That's still not 0, right? There may be problems where you're given pressures and Kc, or you're given concentrations and Kp. And then you have to either convert your K or convert your concentration or pressure.